In my research in water management in South Asia, I've used game theory models to analyze strategic behavior in stakeholder decision making. I'm going to explain the basics of this method. So let's go through the foundations of game theory and how it can be applied to real-world problems. What is game theory? Osborne and Rubinstein say it is a tool to help understand the phenomena of when decision makers interact. It isn't a new method. Modern game theory has been around for over 80 years. When is game theory useful? Well, we use it when we want to study strategic behavior and the outcomes of decision making. And what is important when we use game theory is to think about situations as a game with players, actions, outcomes, and payoffs. So why should we learn game theory? Game theory offers a structured way to think about real-world decision-making and actor interactions. It is a tool to analyze people's strategies in a given problem situation. What is nice about game theory is that it requires few inputs, making it easy to apply even when you have very little data. It helps examine very complex situations by focusing on actor interactions and capturing this in a simple model. Here we define an actor as a social entity, an individual or an organization with an ability to directly or indirectly influence a system in which it has an interest. When can you use game theory? When we 1. Need strategic insights into complex multi-actor problems, 2. When the goal is to understand why certain outcomes exist or are likely to occur in society, and 3. When there is a need to explore alternate solutions in multi-actor situations or identify promising coalitions. Game theory should not be used in a predicting way forward, but it can deepen our understanding of a complex problem. What kinds of multi-actor games exist in the real world, particularly in the water sector? Games can be found in coastal or river basin management, for example, games between upstream and downstream water users. In drinking water management, for example, in the supply of water between rural and urban areas. And in funding arrangements in implementing nature-based flood defenses, rather than choosing standard infrastructure solutions. We have provided references to some examples of game theory applications on each of these topics. Now let's explore some basics about game theory. The main inputs in constructing a game theory model include actors, actions, resources, and values from the real world. In the model, actors become the players in the game, actions and resources define the moves in the game, and actors' values are used to calculate payoffs or utility associated with different outcomes in the game. There are two ways to model multi-actor games. One is through a non-cooperative game theory model in which actors compete for their preferred outcome. The non-cooperative model is used in situations in which actors are unwilling to cooperate in a fixed set of rules and make decisions to benefit themselves. These games are often represented using a decision tree like this. The second way is through a cooperative game theory model. This type of model explores cooperative solutions where actors are willing to communicate, coordinate, and potentially pool resources to collectively find a solution. Take, for example, this 3-player game. Here we have 3 actors who can make decisions either individually or together. The cooperative model helps us explore the payoffs of outcomes where all 3 actors act individually versus bilaterally or multilaterally. In this video, we will focus on cooperative game theory. Now let's explore some solution concepts in a cooperative game. I'll use the example of groundwater monitoring in Bangladesh to explain this. Groundwater is an essential source of water in Bangladesh, yet aquifer data is scarce and spread across different actors. There are 3 main actors who monitor groundwater. The engineers, E, who conduct groundwater assessments when installing tube wells for drinking water supply, the monitoring agency, M, who is the environmental department, and residents, R, who also keep track of changes in groundwater quality and quantity over time. A cooperative model of this problem represents the different outcomes in this game. Outcomes are the different forms of collaboration that are possible between the actors, like actors monitoring groundwater individually versus together. Based on this model, we can go on to explore 3 solution possibilities. Each solution represents what each player can expect to receive in the game. Let's understand these solution concepts. The triangle figure is known as a ternary plot. It is used to plot the solutions in a cooperative game. The solutions from the groundwater monitoring game were calculated and plotted using the software R. The first solution that we will discuss is the core. In this figure, the core is marked in yellow. The core is a space where actors can enter voluntarily into cooperative agreements with other actors. In the core, the 3 actors can expect to receive as much payoff as they would from acting individually. So there is a benefit from cooperating. In the core, there can exist numerous possible cooperative solutions. The core is not a specific solution to the monitoring problem, but more a depiction of the voluntary solution space. The second, more specific solution concept that we calculate is called the nucleolus. In this solution, all players are considered equal. The nucleolus is a solution that makes the most unhappy actor less unhappy without negatively affecting the other actors in the coalition. So here we offer the most unhappy actor some utility to stay in the coalition without hurting the others. In this game, the nucleolus is located within the core, which means an egalitarian solution is possible through voluntary cooperation by the players. If the nucleolus fell outside the core, this would mean an egalitarian solution is not possible without incentivizing the actors. The Shapley value is the third solution concept. This solution is representative of a fair solution. This solution may be pursued if the actors hold fairness as an important normative value in the problem-solving process. Here, payoffs are distributed in a coalition based on what each actor brings to the table and how the coalition is formed. Given our understanding of this method, let's think about what it offers to building with nature. Game theory can serve as a starting point for exploring cooperative potential in building with nature. For example, who are the actors in the project? What do they care about in potential building with nature projects and designs? What added value do they bring if involved? How can the actors cooperate? Which coalitions are feasible? And how beneficial is cooperation? So cooperative game theory can be applied in building with nature. The method works best with a limited number of players, typically between 2 and 4. But this simplified decision-making context offers insights into the actors in the design and implementation of building with nature projects. If you want to learn more about game theory or its application methods, you may want to refer to these resources.